Hello, I'm Soumick and I'll be presenting our work DS6, Deformation-aware Semi-supervised learning, application to small vessel segmentation with noisy training data. Small vessels in the brain, such as the LSA, are the terminal branches of the arterial vascular tree, responsible for supplying blood to the basal ganglia. Pathology of these small vessels can be associated with aging, dementia, and Alzheimer's disease. Segmentation and quantification of such vessels are crucial in the study of cerebral small vessel disease. Advancements in the field of time-of-flight imaging using 7 Tesla scanners unleash the capabilities in depicting such small vessels in a non-invasive manner. Manual segmentation can be very reliable, but it is time-consuming and laborious task. Semi-automated techniques also require manual efforts in parameter tuning. Non-deep learning approaches as Frangi can detect medium to large vessels based on structural properties, but often face challenges while detecting the small vessels. On the other hand, deep learning based approaches can perform segmentation without manual intervention, but they typically need large datasets for training. Among the various deep learning models, U-Net and its flavors like Attention U-Net, U-Net Deep Supervision have been the go-to networks for segmentation. Bortsova et al. Proposed a semi-supervised model based on U-Net for 2D segmentation of X-ray images, which handles the problem of small datasets really well. This work shows that the deformation consistency is better than using deformation as an augmentation step. Here we proposed a modified U-Net Multi-Scale Supervision model where the loss is calculated not only on the final output of the model, but also on 2 outputs of the internal layers. These additional outputs are first supplied to fully connected convolution layers, and then they were finally interpolated to have the same size as the output. All these 3 outputs are used for loss calculation, and a weighted sum of those losses are used as the final loss value, and then it is backpropagated. Now, to make the model deformation aware, a Siamese architecture is used. There are 2 different types of loss used in this DS6 approach. First, supervised loss is calculated by supplying the original input volume to the model and comparing the output against its corresponding label. And the second supervised loss is calculated by supplying a deformed volume to the model and then comparing the output against a deformed version of the corresponding label. Finally, a consistency loss is calculated by applying the same deformation on the first output and comparing that deformed output against the second output. A sum of all these 3 losses are used for backpropagation. For validating this approach, we used a 7 Tesla TOF dataset consisting of 11 volumes with 300 micrometer isotropic resolution. 6 volumes were used for training, 2 for validation, and 3 for testing. 3-fold cross-validation was used to evaluate the generalizability of the model. Labels for this dataset was created in a semi-automatic fashion using Elastic, which resulted in a noisy annotation as can be seen here. We've used a patch size of 64 cube. The loss was calculated using Foucault-Travasky loss and was optimized using the Adam optimizer with a learning rate of 0.01 for 50 epochs. Mixed precision training with batch size of 20 was performed using NVIDIA Apex. Now, for applying deformation, a differentiable version of the Torch.io's random elastic deformation was created using 3D B-spline kernels with a random number of control points, maximum displacement of 0.02 with 2 locked borders. We compared our results against 2 non-deep learning based methods, Frangi and MSFDF pipeline, which required brain extraction and bias correction as pre-processing. We also compared our results against 2 deep learning based methods without applying any pre-processing. And those methods are U-Net and Attention U-Net. Now, here are some results while comparing them against elastic labels. White signifies correct segmentation, red denotes under, and blue denotes over segmentation. It can be seen that the deep learning techniques perform better than the non-deep learning techniques. But the differences among the deep learning techniques are really minute, and it is really difficult to understand them from this figure. So let's have a look at the numbers. It can be seen that the deep learning based techniques outperformed the non-deep learning ones. Moreover, U-Net MSS performed better than U-Net. And finally, we can observe that both U-Net and U-Net MSS performed better with deformation-aware learning. Our proposed method DS6, which is the U-Net MSS with deformation, performed the best among all the experimented methods. However, the elastic labels are noisy and warrants for comparing the results against manual annotation. It can be seen that the deformation-aware models perform better than the models without deformation. Quantitatively, the elastic label only achieved a 50% dice while comparing against manual annotation, and the proposed DS6 model got the best dice in this mix, achieving a dice of 62%. Now to conclude, the proposed method outperformed the baseline methods and did a better job in segmenting the vessels while being trained with noisy labels. A possible future work would be to incorporate the maximum intensity projection as an additional loss term to improve the vessel continuity. The code of this project is available publicly on GitHub. Thank you so much for your attention, and feel free to contact me for any questions or feedback.